Hey everyone, welcome back to my daily coding series. Today is day 81. So I am going to go back and try to do some of these hard problems from the roadmap here. So we're going to look at trapping rainwater, which is a hard two-pointer problem. So I've tried it in the past, but I just basically commented that all out and haven't looked at it. And I probably did that several months ago and I remember absolutely nothing. So let's take a look at it here. So the problem is we are given an array of non-negative integers which represent an elevation map. Each value, height of I, represents the height of a bar, which has a width of 1. Return the maximum area of water that can be trapped between two bars. So this is an example. So the first one is a height of 0, and then 2, and then 0, and then 3, and then 1, and then 0, and then 1, and then 3, and then 2, and then 1. And we have to return the maximum area of water that can be trapped between the bars. So right off the bat, it looks like there's no water here, so that means there are no walls on the end. There is a floor. So basically we have to make certain shapes that hold water. So I guess a theory would be like identify shapes or regions that hold, and then calculate how much each region holds. Okay, so when it comes to, and yeah, just a reminder, this is not a tutorial channel or anything. It's just a live problem solving process. So, okay, so to identify the shapes or regions that hold water, so I'm thinking of like which kind of shapes it might be. So something like this, which is like a cup. But then of course we could have something like this. So it's like multi-layered. We could have this, like this could be optional. So if this is here, then we unlock this. Otherwise, we just have this. So it's almost like we're looking for the cups. So this is kind of like a cup. So the water almost becomes like the floor for this water to exist. So in each region, there needs to be two walls. And then, for instance, if we had this, okay, so water I'll do as like W or something. So in this case, the water only goes to the minimum height. The water only goes to a minimum height. So if we just had one like cup, we would basically just take the minimum height So I think it's like identifying the goalposts, I guess, or like the walls are really important. And then maybe you can just go like one at a time. So for instance, here, if we had these two, so we know this is the highest. So then we'd find anything that's on its level. And if it is, then we know that this whole area should be filled. So anything between this should be filled. So we'll just look, okay, this one, we take like this height minus this height, and that would be 1. This height minus this height, that would be 2. And then once we reach here, then we're at the end. So what if, okay, so that would work for that, but what if this wasn't here? So if we had something like this, and this of course has to be there as well. So in a case like this, you would see that nothing has this height to the left. And then in this case, you would see that this has its height to the right. And what if this was flipped? Like, what if we had something like that? So I think it doesn't matter if you go from the left or right. So I'm thinking if our first pass identifies like cups, which are basically just like the walls, maybe identifies walls. So what you would say is, I guess I'll just do while I is less than length of height. So maybe you would have like, I don't know. So maybe we'd have like a dictionary, like walls or something. And what I'm thinking is, so before I code it out, I'm thinking maybe we can, how we'd store it. So if we look at this one, 0, 2, 0, 3, 1, 0, 2, 0, 3, 1, 0, 1, 3, 2, 1. Okay, so in this case, I'm thinking what we can do is, so if it's not 0, we can remember it. So, okay, so 0 we just skip. 2 we can remember. So we'll say that there is a wall of size 2. And we'll see, is anything that we encounter greater than that size? If it's less than, so there's like so there's 3 cases. Greater than, equal to, or less than. Okay, so 0 we skip. 3 is greater than, so that means we just found a new like wall pair between index 1 and index 3. So that's a wall pair. And then we replace our current wall that we're looking for to 3. So now the question is, where does 3 match? So then we'd go 1 is less than 3. So now we also, I think, should store 1 because if the, yeah, so let's say we also store 1. And then 0, and I should explain. So the reason is like if this was infinity, right, or if this was like something really high, we may never find anything that's greater than or equal to it, but we're still interested in this wall. Okay, so then we have 3 and 1. Now we have 0, which we ignore, and 1. So there is sort of a connection between this one, which is 0, 1, 2, 3, 4, and 4 and 6. So there's something there with, we know that there will be something formed at 4 and 6. So I'll just write it down. Okay. And then we get to 3. So 3 matches with this 3. So then if we look, it was 0, 1, 2, 3 until 7. So that's like another wall sort of thing that we have. And then, so now our current wall is 3. So 2 and 1 are both less than, so we'd record them to see like if we find a wall that's, you know, like that, but then we run out. So then we would be left with this. So 1 to 3, 4 to 6, and 3 to 7. So really what we do we really only want 1 to 3 and 3 to 7. Okay, so I'm thinking, yeah, step 1 would be identify walls. And then step 2 would be calculate it. So let's say we did have these walls already. So we'd have, and maybe we should store like its index and its height. So, so we could say like this. So the first wall, so it was 1 and 3 were the indices. This one had a height of 2 and this one had a height of 3. And then if we look here, so it was 3 and 7. And then this one had a height of 3, and 7 also had a height of 3. So this is like the information. So it's a list of wall pairs. And what we would do is, so we'd start here. So I guess what we would do is make a function that takes in a wall pair and then calculates its area. So we'd have like define calc water, or like get water area, which takes in a wall pair and the height. And then what this would do, so I'm gonna write this function assuming that we have this data. And then if we can get this data, then, so I'm going to assume we already can do this part. So what this would do is, so I'd say I'd set I equal to wall pair of, okay, first of all, I'd say left wall equals wall pair of 0 and right wall equals wall pair of 1. Okay, so we have that set up. And then I would say, so we want to start I at this one. So we'd say for I in range, we'll start it at left wall of 0 and go till right wall of 0. So it's the heights. So if I were to print I, and this is the great thing about writing functions like this, is now I can just test it with the information. So I'll just say like temp, and I'll pass in temp and height. So now I want this to print basically, so we only want to take in one wall pair. So if I just say temp pair is just this part, this data structure doesn't make sense. Okay. Okay, so then I want this to print 1, and then this should be +1 actually. So it should print 1, 2, 3. 1, 2, 3. Okay, perfect. So now what we want to do, so we'll have a variable called water, which we'll set to 0. And then, okay, so for the wall, so then the water ceiling, so the highest that the water goes up to is the minimum of left wall 0 and left wall 1 and right wall 1. Okay, and we actually don't really want to include even the walls themselves. So maybe we should do just +1 and this. So this would give us just 2, and that's what we want. Okay, so what we're going to do now is water plus equals. So it's going to be for every, we're going to take the water ceiling and subtract it by heights of I. So whatever the wall is, so in this case it'll be 0, and then it would return water. So if I print this, it should print, in this case, 2, because it'll be water ceiling, which is 2. So it'll be water plus equals 2 minus 0. I added an extra S by accident. Okay, 2, perfect. And if I were to give it, let's say, this part, the area here now should be equal to, let's see, 7. It should be 7. 7. Okay, perfect. So this function works, and it really just takes O of n, really, because, well, it takes the time from one index to another, but the way that our data is structured is that the walls, we can't give this function more than anything that would result in more than a linear time, because the walls all exist within the the array. Okay, so now we have this function which works. So now the question is, how can we turn this array into wall pairs? So now the question is like, how to turn height list into wall pairs. So I guess I could say like identify wall pairs, and this will take in height and it will return wall pairs. So wall pairs, we know, is going to be, so I need to definitely think of the algorithm on how to do this, but the idea is it's going to be a list of wall pairs. Yeah, it's going to be a list of type wall pair, and each wall pair is made of 2 walls, and every wall is a height and an index. So that's the idea. So now let's think of the actual algorithm on how to do this. So we're at 16 minutes. I have a feeling that this is going to be the hardest part, because there's a lot of edge cases, it seems like if you have 2 walls right next to each other. And okay, so I liked what I was doing before about how okay, so we can delete this and this, and then we can delete this as well. That's my old code. Okay. Okay, so when it comes to identifying walls, there is something interesting that I was thinking about. So we could have a structure like this, right? So this is an interesting structure to keep in mind. We could have a structure like, and I think instead of hashtags, I'm going to use a different, actually hashtags make sense. Okay, so we could have a structure like this, which is important, because if then you have like this, you basically need to know like what was the minimum I had so far. So I don't know if this reminds me of a stack at all, but I'm thinking what you could do is have a stack, right? And every time you encounter a new highest height, so maybe we have like a stack, and every time we encounter a new highest height, we add it to the stack. So it would be like 3 and then 2 and then 1. And then once we encounter something that is bigger than the top of the stack, we continuously pop from the stack until it's no longer bigger. Because just the nature of how it's, this nature where it's kind of like you're matching each wall, it almost feels like. So in this case, we would add 3, we'd add 2, we'd add 1. And I'm just assuming this is the floor. And then okay, so then we could have something like this. So when we get to this point, here, we have something of 1. So we would pop off the stack until we get 1. And then, so how would I know to hold off until the next one or not? So you'd have to almost look ahead. And I know this is a 2-pointer algorithm. So I'm thinking of maybe you could like have a pointer here and here. Yeah, so let me think about it in terms of pointers. So I'm going to go back to the original case. So if we had 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm just going to draw this out quickly because I think it will help me a lot. So this one is 0, this one is, whoops, I muted. Okay, and this one is 2, and this one is 3, and then we have 1, 1, like that, right? And then 1, 2, 1. Okay. So in this case, if we think about it with pointers, so if we had L and R, I'm almost thinking if we just like start in the middle. So what if we started, so how many is there? 10. So we would start at, let's see. So there could be 4 on each side. So I'm almost thinking you could start in the middle. No, but maybe actually. So maybe you could start in the middle and just keep like growing. That doesn't seem right. Okay, so as a human, how am I doing this? So, okay, so right now we don't know any information about whether or not this is a wall. Like whether or not this is a cup. Well, I guess because this is height 0, we can move it. Okay, so because it was height 0, I moved it. So this could be a cup. These could be walls. So how do we know it's not? Well, I guess we could act as if it is until we see that it's not. So we would know that this is not walls if we find something that's bigger on either side. But then how would we know? I think that I kind of liked what I was doing before with the 3 and the 2. Like that made a lot of sense to me. If you just go from, and maybe we'll need another pointer later, but so far I think it makes a lot of sense to me that we just have maybe like, you know, current, like unopened walls, or like unclosed current left walls maybe. So 0 we'd skip. Here is 2. So we would say, okay, we have a left wall of 2. So if we find something that's bigger, so the first thing that we find that's bigger than 2 must be a wall. Unless, yeah, that's always true. Okay, so then 0, we don't count. Sorry, let me just silence my phone. Okay, sorry, I was just making sure it wasn't important. Okay, so 0 we don't count. Now we're at 3. So this is the first thing that we found, the first height that we found that's bigger than 2. So we know that it must be a wall with 2. So then we'd record that. So walls would be, so we found a wall pair, and that is index 1 of height 2 and index 3 of height 3. Now though, our left wall that we're looking for is 3. Okay, so now we find 1. So this is where it gets interesting to me, is when you find something that's less than your height. Because you somehow need to be able to look ahead and see. Yeah, so this is the interesting part to me, is like we could so if we use our current definition of what we're doing and we just like take another one, maybe that's where you need the 2 pointers. I don't know. So if we store 1 and then we find this, so this tells us we don't really know without looking ahead. So I mean, I could think of an n squared. Maybe I should start with an n squared solution. So what we would do is, when we find this 3, we would see the largest. Basically, we'd see like, where does this end? What's the largest thing up until that point? So it's almost like if you knew at every left wall where its right wall was, then you would be fine. So in this case, we would find this wall, and then we would see, okay, what's the, so then we'd scan through everything. When do we hit a wall that's greater than or equal to this? And then we just record it. Then we get here and we say, okay, let's scan through everything until we hit a wall. So in this case, we would basically keep scanning until we hit this. And then when you get to that, I think you can just move your pointer up to here, because you know that this is a wall, so anything in here doesn't matter. So then you would move your pointer up here, and then here you'd say, okay, there's no wall of size 3, there's no wall of size 2, there's no wall of size 1. So why don't I try doing that? So this will be n squared, but it's always good to start with that. So my idea is, so we'll have, didn't I make a, yeah, this. So my idea, so I'll get rid of this, is that we'll have a pointer, I'll call it I. So it's going to be equal to 0. And this may not be true, but okay, so we're going to have something called like left wall. Yeah, so I'll just say, first of all, if height of I is equal to 0, I'll just skip it. So if it doesn't equal 0, yeah, so otherwise, if it doesn't equal 0, then what we'll do is we will keep looking. So like here, okay, it doesn't equal 0. So we'll set j equal to I, and then we'll say while j is less than the length of height, we're going to keep going. So j is going to keep going up by 1. And if height of j is greater than or equal to height of I, then we've found a wall. So in this case, we've found a wall. So in that case, when we find a wall, we should, so let's have wall pairs. So we'll say wall pairs dot append Yeah, so we'll append two tuples, and it will be I height of I and j height of j. Okay, and then what we want to do is we actually want to set I equal to, I think, j. So we want to set I equal to j now and start searching from there. I equal to j, and then we'll exit out of the while loop. So I will become whatever j is. Okay, so now there's another case. So what if this exits, and if j equals the length, and then, so if j equals the length, then we'll just go up normally. So if j equals length of height, so that means there was no wall. There was no wall, so we'll just add j will go up by 1. So either I becomes j or I goes up by 1. Okay, so let's just play with that and see what that gives us. So how much time am I at? 30 minutes. Identity wall pairs. Identify. I always say identity. Identify wall pairs. It should just return wall pairs. Okay. So now in our kind of main function there, let's say here, print identify wall pairs, and we'll give it height. So let's see what that does for us. Okay, we have an infinite loop. Oh, it's this right here. It could be also this, but that was definitely going to cause an infinite loop. This may give us the wrong answer, but hopefully it will cancel the infinite loop. Okay, so now we have a lot of walls. So that kills the program. Okay, so my idea is, so let me print here, left wall found at j. I didn't do f-string. Okay. So now we're just kind of debugging through it. So we find a wall at j equals 1. And then let's say here print added wall I equals j equals. So we're going to go from I to j. Okay, so this is incorrect. So it's probably because this will always be equal because we're setting j to I. So we really want to set j to I plus 1. Okay, so we found a wall. So left wall found at 2 to 3. We add wall from 1 to 3, that's correct. And now it should exit the loop at that point. So let me up here, I'll print. Okay, so let me just run that again. And this doesn't necessarily mean there's a wall found because we could be repeating. Okay, so when so now So let me do what I initially intended. So if j equals length of height, then I will go up by 1 only. So from 3 to 7, that's right. Okay, so we got it. So that looks good. For now. Okay, so then we would say wall pairs equals identify wall pairs given height, and then we'll say for wall pair in wall pairs, total water plus equals get water area for wall pair. All right, so let's try something like that. So this part's pretty janky, but all right, that's because I'm doing this too soon. All right. And we also have to pass in height. Okay, so the first case got accepted. I'm not really expecting this to work for everything. Okay, so let's see here. 4, 2, 3. Yeah, so in this case, 4 never finds anything. Yeah, so if we have 4, 2, 3, so this doesn't work because when 4 never finds anything, it goes to 2, and then 2 finds 3, and then it thinks that this is the wall. Yeah, so this may be where we need the two-pointer approach because with something like this, it would make sense to me that so maybe having the walls we had 0, 2, 0, 3, 0, 2, 0, 3, 1, 0, 1, 3, 2, 1. And then now we also have access to this test case 4, 2, 3. So what if you had 2 pointers, and then so maybe you could just move the one that's smaller. And again, all I have to do is just identify the wall pairs at this point. This part will work. So all I have to do is just identify the wall pairs. So maybe we'll just store, I don't know, like current wall or whatever. So we'll have 0, 1. Now we'll move the one that's lower and we get 2, 1. So because this was bigger, we'll update it. So now 2, 1, so we'll move this one in, and because that's bigger, 2, 2. Right, so now they're the same, so I'll just move the left one. So because that's smaller, this is still our leftmost wall. So I'll just continue moving this one, and now we found a new leftmost wall of 3. So in this case, I wonder almost if we should store these as walls because we've gotten that information. If we find something bigger, so at this point, so our wall is 2, 2. So like, I'll just say left max is 2 and right max is 2. So okay, so now I'm going to keep track of these variables. So we have left max. So right now they start at 0 and 1. So because 0 is less than 1, we'll move it up, and now left max becomes 2. Right max is now 2, so technically there's a wall there. but it has no space. So I don't know what to do about that case. Okay, but so we'll continue. So let's just move left. So left max is still 2. So maybe we should just keep bringing this in until we find a new wall. And if we don't, then we just use the one that we already found. So would that work? Let's try it. So then once we find 3, we know now that there is a wall pair from 1 to 3, and our left max should now be 3. So now we'll move this in. So we kind of found another like container that doesn't really hold any water from 2 to 3. And now the right max is 3. So in this case, I guess I'd move this, and then I'd move it again, and then I'd move it again, then I'd move it again. And then once L and R touch, I guess, that's when you know that you found it. So then okay. So let me try, so that would, with this example, if we have L and R, basically you would store left max and right max and then just keep moving R until they touch and you'd get 4 and 3. Let me make up another example here. So if we have like 5, 0, 3, 2, 4, or say 3, 4, 7, 6. Okay, so in this case, I'll have left max and right max again. Okay, so because yeah, okay. So because left max is 1 and right max is 6, we'll move this one. Because we basically know that, okay, so we've updated it, but because the difference is 1 only, we'll just ignore it. Like, we shouldn't actually get the water of that area. Okay, so now, so left max is 5. So then we go to 0. We go to 3. So none of these are bigger than left max. And we wouldn't be searching any of these. So this is kind of interesting. So if this was 4, for instance, then we wouldn't be searching these. So we're only searching these because we know that there is a wall on the other side. 3, 2, 3, 4. Right, so all of these, we actually know there's a wall at the other side. So then when we get to 7, at this point, left max becomes 7, and then we store that wall that we just found. So we'd say there's a wall between index 1 and 2, 3, 4, 5, 6, 7. Yeah, so now we know there's between index 1 and index 7 that there's a wall. And then right would move in, and that would be that. So what if there was a 0? Like, what if we had 0, 1 here? And then let's just say 4. So how would this change it? So that would work with, so 1, 5, 0, 3, 2, 3, 4, 7, 6. So this one worked. So let's try with this. So left max is 1 and right max is 4. So we'll move this in. Left max now becomes 5. So right max moves in. And now we found it. We update right max, but because the distance between the old right max and this right max is only 1, we don't like add it to our wall pair. Okay, so now this one's less than. So we're going to just keep moving it until we find something that's bigger than left max. And we find it here. So we store a wall from 1 to 2, 3, 4, 5, 6, 7. Yep, and that's it. So then R will keep moving while it's less than right max. So we'll go down, down, and down. So once L and R meets, then we know we found another wall, and this is updated, between left max and right max. So that would give us between left max, which is index 7, and right max, which was at index 8, 9, 10. Okay, so this actually makes a lot of sense to me. So I'm going to try implementing that. So I'm just going to delete this here. So the idea is you have two variables, left max, which will just start as height of 0. And you have right max, which starts at height of 1. And then, so while L is less than R, that would be -1. So say L equals 0 and R equals length of height -1. Okay, so, and once they're equal, then we should stop. Okay, so while it's less than, so there's two, I guess, possibilities. So if left max is less than or equal to, and then so we want to store the height, but we also want to store the index. So let's say L, so just 0, and this would be R. I'll just do L for consistency. I'll just make it 0, I guess. Okay. So while L is less than R, so if left max of what? Of the height. So if left max of 1 is less than or equal to, so if it's less than or equal to right max of 1, then we know we want to move L. So we want to just continuously move L. So maybe we could do a separate while loop in here, or maybe we could just say L plus equals 1. Otherwise, R plus minus equals 1. So they're going towards each other. So we could say if, so we want to update the maxes. So either one could move, I guess. So what we want to say is if left max of 1, so if the height of left max is less than, what about equal to? I guess, or equal to, of current, so height of L. So if we just found a new max or equal max, then in this case, we found like a wall. So let me say wall pairs. So we want to add, so in this case, we found a wall. So we'll say walls dot append. So from left max, so left max is a wall itself, and then the other wall, which will be L and height of L. Yeah, so we'll just add that. And then same for the right. So if right max of 1 is less than or equal to, but only if, the difference. So, and L minus, so L minus the left max of 0, so the index of left max is greater than 1. Because if it equals 1, then there's no space in the middle. Okay, so similarly, we'll say if the right max height is less than or equal to the height of R, and R, well, in this case, so R is actually greater than, so I might have to do like a less than sign. So if right max, so if, yeah, so we'd update it. So, and R, it minus right max. So like, let's imagine that this was 15. So when we're here, right max is 4, then we decrement it. Now R minus this, so it would be like 5, let's say, so index 0, 1, 2, 3, 7, 8, 9, 10. So it'd be 10 minus 11. So it has to be greater than -1. Because here it would be, so if you did, so maybe we should just do right max of 0 minus R has to be greater than 1. Okay, in that case we would append it. Okay, let me try this and see what this looks like. And then of course, actually, so when L and R finally do meet, we want to append left max and right max to the walls as well. Okay, so let's call this function with height. And then I want to append this as a tuple. Okay, let's see what this looks like. Okay, we have 0, 0. Zero, zero, 2, 0. Let me do it as a, can I do it like that? So can I append a list to it? So it may make it easier. Okay, I muted myself for a second there. So we're going to have this tuple and this tuple. Let's see if that makes that easier to read at all. Okay. So it's saying 0, 0 to 2, 0. 0, 0 to 3, 3. So why is, oh, because I'm never updating left max. All right, and then we want to set left max to be equal to the tuple L and height of L. And then here we want to set right max to be equal to R, height of R, like that. So let's see. Yeah, all right. Let me just print what L equals and what R equals. We're at 54 minutes. So we're at 0, 9. Then this moves up 1, 9. Okay, then it goes 2, 9, so that's not how it should be. Print left max. So height 0. So left max doesn't get updated, I guess. Left max. Okay, yeah, so I want to update left max no matter what, but only if that's different should I add the wall. So I'm thinking something like this may help. So we're updating. Well, maybe the order actually matters here. Like this. So we want to update left max no matter what, but we only want to append a wall if that's true as well. Okay, there we go. And we have the walls now. So what if I were to do wall pairs with 4, 2, 3? So this should give me just the wall pair, just one wall pair, 0, 4, and 2, 3. Okay. So let's yeah, so this code still should work. So we'll say wall pairs equals identify wall pairs with height, like that. Let's try. Okay, let's submit it. Not expecting it to work right away. Okay. So we're off by 1 here. All right, I'm going to delete this stuff. Okay, so let's take a look. So we have 0, 1, 0, 2. Okay, so I'm identifying the walls. Let's see. So let's see. I'm guessing this should have used it as a test case. I'm guessing that this function is the problem. Okay, so I have identified the walls at 1, 1, so that... Oh, okay. And then let me just print heights right above there so I can see better. Okay, so it's saying that at index 1 till index 3, there is a wall. That's true. That is true. Then it's saying from index 3 till index 7. So 3, 4, 5, 6, 7. That's also true. Then it's saying from index 7 to itself. So that's obviously not true. And then index 7 to index 8, which also is not true. So let me see this one that it's adding. Because maybe that's not really how it should be. So we're adding 7, 3 to 8, 2. Yeah, can I actually, does the program still work if I don't do that? No. Okay. So now let's see. So now it's still doing 7, 3 to 7, 3. So 1 to 3 is good. 3 to 7 looks good. But 7, 3 to itself doesn't. So when is it adding that? So now I feel like it should still, so okay, so here it's 1, area of 1. Okay, let me pass, so let me isolate the problem here. So I want to call get water area, and I want to pass it this height. And then I want to pass it wall pair is a list from, so it's going to be 1, 1 to 3, 2, and then 3, 2 to 7, 3. So I want to see, so it's mine's 5, it's expecting 6 though. So what does this print? Is this also in a tuple? I don't think so. Alright, that experiment did not work. Maybe I should have just copied it from here. Interesting. Concatenate tuple not into tuple. So this is being read as a tuple plus integer. Left wall is a wall pair of 0. Yeah. Oh, because it takes in a single pair. That's why. Okay, so well pairs make this, and then, okay, that should work. So we didn't return anything. What am I trying to do? Yeah, I want to return total water. I want to see if this is causing the error. Okay, so now my output's 9. Okay, this is like the worst testing of all time, so I'm sorry about that. Okay, so let's see. So let's comment out this, and let me just say wall pairs of 0, and see what that gives me. So this should work now. So it's 2. So it should actually only be 1, right? And then this one gives me I think I copied the wrong. Yeah, really bad testing, but it's all right. So case 2, I want these wall pairs. Okay, that was the problem. Yeah, okay. So now comment these out, comment this back in. So of this first pair, it should be, so it's printing 1, which is correct. Okay, so it's printing 1, which is correct. So we see from 1 to 3, it should be only 1. All right, and now for the second one, it's printing 4. Is that correct? So it's printing 4. So from 3 to 7, 0, 1, 2, 3, 7. So the ceiling is, so it should be 1 plus 2 plus 1. Sorry, yeah, 1 plus 2 plus 1, which is 4. So it should be 4. And then I want to see, is this what's causing the issue? Or is it just 0? It is just 0. So when I call it, it's giving me 6, but that's not. My output's 5. But it's expecting 6. Oh, I think it's because of this wall right here. So there should actually be a wall here when R so it could be this condition here. So let me print write max updated with R equals. Okay, so I want to see updated with R equals, so height equals 2. So it updates it at 1. Okay, here it is. So it updates it at 1. Updates it at 1 again. Oh yeah, I guess if it's equal. But here, it's just stalling on this one, I guess. Okay. So it keeps doing 1, and then when it gets to 2, it updates it. So it should, let me see. Let me print this. So is it ever greater than 1? So 0, 0, 0, 0, 1, 2. So it should add a wall. Ah, I see. I'm adding, it's just a typo basically. R height of R. So now we should have the, okay, now we also have from, and in this case we might actually want to reverse it. So we'll say from here to here. So that's a tuple and this is a tuple. No. Why is it red? We want to append the list. So now, okay, so that fixed it. All right, let's see if that works. I have a lot of print statements, so it's going to take a long time. Okay. So it says success. Let me get rid of all this stuff. How long are we at? 1 hour, 10 minutes. Okay, let me try again. Okay, let's try it on LeetCode. I'll just delete this old stuff. Okay. So this one is called Trapping Rainwater. Trapping Rainwater. All right, let's see if my solution works here. Yeah, okay, awesome. So we have a solution. The memory, you know, I feel like this stuff isn't, I'm kind of learning, like, the more I do real projects and code is like, this stuff doesn't matter as much as like testability and changeability and stuff like that. And not to say that my code even has good either of that, but I'm not going to focus too much on this. But the memory is interesting. It's pretty obvious why that's happening. So this stores everything, and you don't actually really have to, I don't think. You might be able to just do it with the pointers. But either way, yeah, I'm glad. This is I think this is the first LeetCode hard I've actually solved. I did one, but I didn't do it the right way it was supposed to. But this is like actually, I think this is my first LeetCode hard I've solved. So, and it's really the first one I've tried. So I'm not sure if like an hour and 10 minutes. Usually I try to go for like 20 to 30 with the medium ones. So, but yeah, I'm really happy I was able to solve this. It's a cool problem. Yeah, and here, a lot of typos. Not actually only one typo, but sometimes it's hard to get lost into the details. I kind of liked my problem solving approach and how I was breaking it down into functions. I really liked how I got this part out of the way early. So we just wrote this function and assuming this part was already done. So then the problem went from the whole thing to just identifying where the walls are. So I really like that approach. Yeah, so today was day 81. Thank you guys for watching. And I will see you tomorrow for day 82. And thanks for watching.